All right, guys. So this is the topic that because we got school canceled for a couple days because of our transition to hybrid, we don't really have time for this all together. But of all the things we're doing this unit, I think that this is the most straightforward topic. We're going to spend another 2 chapters later at the end of the year going through this way more in depth. So for now, we really just need to know the very basics of identifying acids and bases, and then a couple, like one type of acid-base calculation that's really honestly pretty simple and very similar to what you guys already learned in a previous lesson. So we're going to go through this just in this video, and I'm hoping the video doesn't take too long, but it's just something you guys can do on your own, and that'll prepare you for the test on this topic. So just basics, acid, bases, and electrolytes. So acids, when they dissolve, they form hydrogen ions. So as you can see down here, we've got hydrochloric acid. Where's my pointer? There it is. So we have hydrochloric acid, and it splits up and makes this hydrogen. So what acids do is they form hydrogen. So as we can see, we make hydrogen, we make hydrogen, we make hydrogen. And strong acids fall apart completely, which means that they fully split into all of their ions. So like HCl fully splits into hydrogen and chlorine. None of them stay together, none of them are bonded once they get into the water. So these are all, remember, they're covalent compounds because hydrogen's a nonmetal. But in solution, they fall apart into ions. So that's one characteristic of acids and bases, is that they're covalent compounds. These ones are covalent compounds, and they split into these ions. Okay? So bases, on the other hand, they're more ionic, honestly, but they either split into hydroxides, or we'll see later they can accept hydrogens. But if you ever see something with a hydroxide on it, it's always going to be a base in water. But it has to be in water for it to act as a base. As a solid, it doesn't really do the same stuff. So strong bases dissolve completely into these two ions, okay? Okay, so when we're thinking about acid-base reactions, we're looking for something that's donating a proton, which is a hydrogen. So when it says a proton, what it really means is a hydrogen ion. Because if we just think on the side for a second, hydrogen usually has 1 proton and 1 electron, and actually usually it has no neutrons. So if I make it an ion and I get rid of this electron, it's just 1 proton. So a hydrogen ion and a proton are the same thing, so we can use those words interchangeably. So an acid is something that's donating protons, and a base is accepting those protons, and it's usually hydroxide, but not always. So let's see this idea. What is the reaction of HCl and KOH? So I have HCl and KOH. Whoa, that's an H. KOH. Okay? They are going to make KCl. So this is also, it's kind of like another double replacement where we're swapping outside and inside. But instead of writing HOH, I'm just going to write H2O. Okay? So that's what acid-base reactions look like. And you'll notice that the hydrogen is going from one compound to the other. It's going to that OH. Now, if we're looking at just the net ionic equation, then things that are spectators are going to not react. So if we think about what this looks like with a complete ionic equation, it's H plus and Cl minus plus K plus OH minus, because they're in water already. So we're assuming in these cases that we're starting with an acid and base that's already dissolved in water. Remember, because they say aqueous here. And then they're going to make our K plus and our Cl minus, which is a soluble salt, but then water stays together. So the key for these, in precipitation, the solid stays together, but in acid-base reactions, water stays together. So if we cancel out all those spectators, we just end up with this basic net ionic equation. Every strong acid, strong base reaction has the same net ionic equation. For now, that's all we really need to know, but later when we get into like weak acids and weak bases, it changes. But for now, whenever we do this, anything that's attached to the hydrogen and the hydroxide is going to end up canceling out, and it just becomes that water. So here's another example, right? So we have a strong acid and a strong base. So we do the double replacement reaction, and then we get NaCl, which is still aqueous, and H2O. Now remember, anything aqueous splits apart, so all these float around as ions, but the liquid stays together. So that turns into my net ionic equation here. Okay, so when we're identifying acids and bases, there's something called a conjugate acid and a conjugate base. So when hydrogen, acids lose that hydrogen, they turn into what's called their conjugate base, because that base could add to a hydrogen and go back and make that acid. So it could act as a base and accept that hydrogen. And same thing with bases. When bases gain a hydrogen, they turn into a conjugate acid, because now this H3O plus is something that could lose a hydrogen and go back to make H2O. So when an acid loses its hydrogen, it becomes a conjugate base, and when a base loses an acid, when a base gains a hydrogen, it becomes a conjugate acid. So let's identify. So the first thing we have to do is figure out which one of these is our acid and which one of these is our base. So these two are always our reactants, and then these two are always our product. Oop, that's R. These two are always our products. Okay, so this look here, this turns into this. And there's one of two ways. It's either going to lose an H or gain an H. As we can see, it lost an H. Anything that loses an H is always an acid. And we can look over here between these two. This gained an H. Anything that gains an H was a base. So that means that this is my base and this is my acid. Now in this case the base didn't have OH minus, but if it did, it'd be a really easy way to see. So now we know that the base always turns into the conjugate acid, and the acid always turns into the conjugate base. Here's the way that we know that there's a conjugate acid and conjugate base. If I write the whole reaction backwards, all right, so now we could do the same thing. Let's see, NH4 goes here. Oh, look, this time it's losing its hydrogen, so it's acting as an acid. So that's why we call it a conjugate acid in this equation. And this one would be gaining a hydrogen acting as a base, which is why we call that the conjugate base. Let me just get rid of that so it looks clear. So this would be my acid, and this would be my base. So when we react acids and bases, we call them neutralization reactions. And one thing that we can do to figure out the concentrations or the molarity of the acid and the base is something called a titration. Because a lot of times I know what acid I have, but I don't know the concentration of that acid or base. And so to find that concentration, I can use a titration. So we have something that we know, which we call the titrant, and something that we don't know, called the analyte. And then we find something called the equivalence point. And the equivalence point is when the titrant and the analyte have been put in the right amount so everything gets neutralized. So let's see what that looks like. Almost done here. So here's my example. So down here goes my unknown. And what I do up top is I use what's called a burette. And a burette is basically, it's kind of like a graduated cylinder, but at the bottom there's a little opening. And when I turn this around, it can let drops out. And so I slowly add drops of what I know until I reach a point when everything in here is neutral. And I find that point by either using color changing materials or a pH meter where I can figure out where I reach that neutral point. And I call that neutral point the equivalence point. And at the equivalence point, the moles of the base you added equal moles of acid in the flask, or vice versa. Moles of acid added equal moles of base. So we don't have to figure out the details of this really at this time. All you'll need to know is how to do a little bit of math in relation to the idea that the moles are equal at the equivalence point. The rest of this will get way in depth when we do our 2 different chapters on acids and bases later. So let's just look at just the basic calculation. So if we have some sample of this, which we don't know what the concentration is, the question is, what is that concentration? Now, when we see brackets of a compound, like say NaCl, that means it's referring to the molarity of NaCl, or the concentration. So brackets will always mean concentration from now on. It's like a quick way to write it, so we don't have to write out the concentration of every single time. So we use this equation here, and it looks almost very similar to our dilution equation, our M1V1 equals M2V2. The only difference is now we do have to take into account how many H's and OH's. Because remember, our net ionic equation is just H plus and OH minus, making H2O. So what I really care about is how many H's and how many OH's that I have. And in something like CaOH2, I have 2 OH's, so I need to take that into account on my base side. So the way I'll set this up, nitric acid is, nitric acid, I think it's HNO2. HNO3, okay. HNO3, so I have 1 hydrogen, so 1 hydrogen. So I'll have 1 times the molarity of the acid, which is 0.0980, times the volume of the acid, which was 34.66. Just like the dilution equation, if you leave this in molarity, that's okay. It's going to be equal to the number of OH's, and we see here that we have 2 OH's, times the molarity of the base, which we don't know, which will be X, times the volume of the base, which was the 50 milliliters. And then it's just a normal algebra problem. We're going to solve for X. So the only difference between this and a dilution is that you have to look to see if there's more than one OH or more than one H, you'll have to multiply that side by that many. So let's see. So the easiest type of acid-base equation you need to know right now is the one we just did, but we can do a little bit of stoichiometry with acids and bases, like this problem. So this says we have a certain amount of HCl mixed with a certain amount of BaOH2, and this is asking for the concentration of the excess H+. Now this is a hint that we have a limiting reactant problem here, and we want to find the excess of the one that's left over. So for this case, it's going to be like a normal limiting reactant problem, and the fact that it's acids and bases doesn't really matter that much, but what's helpful to us is that we can write our net ionic equation instead of the full ionic equation, and this is all we need to know, okay? That's really essentially what's happening. I don't have to write the entire equation between HCl and BaOH2, but you can, and you'll get to the same answer either way. But in this case, what I can see is if I know my moles of OH and my moles of H, I should be able to figure out pretty easily which one has extra and find that. So let's do our normal finding moles for molarity. So remember that 0.25 molar equals X over 0.075 liters. That's for the HCl. And then I have 0.055 molar is equal to X over 0.225 liters. So over here for the HCl, for the H pluses, I get 0.0185. Now over here, this is going to find my moles of BaOH2. And I've got 0.0124. Now because though we have 2 OH's, just like we did for normal solutions, if I want to find just the concentration of OH, that's double the concentration of the entire molecule. So I'm going to have to multiply this by 2 to get the OH's. So this is my OH's. And as we can see here, because this is a 1-to-1 ratio, I have extra OH, right? So all I need to do to find out how much extra OH is to subtract. So I'm going to subtract 0.0185 from this, and I get, let's move all this, I get 0.00625 moles. We're almost done, but it's asking for concentration. So this is kind of a tricky problem. So first, remember what we did was we found the concentration of H and the concentration of OH. And if there's more than one H or OH, you're going to need to multiply by that number. And then we subtract the one that's smaller from the one that's bigger to get the number of extra. But now we need to find the concentration. So our last step is just to take the moles of OH extra we just found and divide by the total volume. Now, because we mixed together 75 milliliters and 225 milliliters, my total volume is now 300 milliliters or 0.3 liters. So I divide this by 0.3, and what I get as my answer is 0.021 molar. Okay, so just to help us out, what I'm going to do over here on the side is, and this is our last thing today, if we're trying to find excess H or OH, step 1, find the moles of each ion. Ooh, let's make that look nicer. Okay, and that's the mole of that ionic substance, not the entire compound, just that ion, right? Find moles of hydrogen and moles of OH minus, which is hydroxide. Step 2, subtract. Okay, whichever one's bigger, subtract then the smaller one from that. And number 3, take your extra moles and divide by total liters. Okay? So the tricky part really is just knowing that if we have BaOH2, that means if I find the concentration or I find the moles of BaOH2, I'll have double the moles of OH minus. And that is pretty much all we need to know so far for acids and bases. So as just a reminder, it's just that titration equation, which is just plugging into the equation, or doing this little bit of stoichiometry here. If you need help with any of this, come to office hours and we will review it together. Please try to do that before your exam. But yeah, that's our acids and bases.